A little bit of normal distribution. So interpret what's in the questions to start with. Tennis ball throwing competition, how exciting. Distance throws is modelled with a normal distribution. Normal distribution has a mean of 32 and a standard deviation of 12. Anyone who throws more than 50 metres is awarded a gold certificate. So that's well over the average, because remember the average is 32. So 50 is well over the average, so that's not too bad. Show that to three significant figures, only 6.68% of children get a gold certificate. So if we think about what this is going to look like, okay, we know that the mean here is 32. We want to think about people throwing more than 50 metres, so we want to find out what this area is here. Okay, so I can't look that up in my table. I need to standardise that, don't I? I want the probability that someone throws the tennis ball greater than 50 metres. So I want the problem that this is standardised to 50. From standardised, take away the mean, divide by the standard deviation. And we could look that up. So probability that someone throws, well, not throws anymore, but probability that it's greater than 1.5. If you look up 1.5 in your table, it will tell you 0.9332. Now, as you look it up, you go, well, that doesn't make sense. 0.9, that can't be 0.932. Oh yeah, silly table only gives me the figures to the left. So I know that area there is 0.9332. I know to get this bit, I need to do 1 take away it. So I give myself space to do that. 1 take away that, 0.0668. Remember, we're trying to show that that's 6.8%, so just times it by 100. Gives you 6.68%. 3 marks. Right, a silver certificate is given to any child that gets more than a certain distance but less than 15. Only 19% of kids get a silver. So let's think about this again then. Always thinking of your diagram and thinking about your areas on this question. That's the best place to start. So we know that I've got the mean there is 32. We know that if you're greater than 50 metres, it's only 6.68% of people. And there's some figure that in between this 50 and bigger than the mean, I would think, well, let's just check, 19%. 19% of people. Well, if I've got 6% here, okay, let's say 7, and this is 20%, that's 27% get a silver and a gold. So I still haven't got past halfway, because remember halfway is 50%. So this 19% is probably this area up to here. So that area there and here is 19.1%. Okay, we need to find this distance here. So I can't look up 19.1%, I can't look up 6.88, but if I think of these in terms of areas, I know that that combined gives me 25.78%, which means this area here, so all I'm doing is basically adding up numbers at the moment, taking away from this area here is 0. Well, it'd be 74%, but 0.7422. If you look up 0.7422, it gives you a Z value of 0.65. So some number, this D number, was standardised by taking away the mean and dividing by the standard deviation, which was 12. I don't know why I didn't write 12 there. Which was 12. And it gives you 0.65. Solve that equation and you get 39.8. Now that seems fairly reasonable. Between the 32 and the 50, it's not like 49.2 or something, so it seems quite logical. 39.8 for that one. Okay, last part of this question. What's the chances we're going to choose some 3 children to take part in a tennis ball throwing event? Too exciting. Find the probability that 1 gets a gold and 2 silver. Doesn't say what order. So probability of gold and silver. That could be what happens, or the probability of silver and gold and silver. Or it could be, I suppose, silver, and a gold. Now all of these Gold we know is 0.0668. Silver we know is 0.191, and then silver again is 0.191. Now we know that this is not going to change for that one or that one, so I need to take that and I need it 3 times, so I just times it by 3. That will give us